All right, folks. I think it's time to get started. There's only 4 people here. I don't know what's up with that, but I guess we should do it anyway. Am I missing something? Can you all hear me?
Yeah, we can hear you.
Yeah.
Yeah.
This is really class time, right? I think so. Maybe everyone's all
Yeah.
voting. Maybe I don't know. Um, I want to do some examples from this section. This is about the second derivative and concavity and the second derivative test and graphing curve sketching. Um, a couple announcements for you 4 people. I did grade the tests, so hopefully you'll be able to see your exams in Gradescope. And there was also some mix-up with the videos. I hope everything is fine now, but I sent an email this morning about that. Sorry about that. If you watched the old version was just one of the videos for next week was accidentally labeled incorrectly. So sorry if you watched that. It wasn't a total waste of time, but it wasn't what you were supposed to watch for this week. All right, let's just do some examples. I got one function actually that I want to try to answer several different questions, but I'm going to use this function for all of them. X cubed minus 3x squared plus 1. So this week's stuff is about well, the three different topics worth. Let's first try to find intervals where it's concave up and concave down. All right, this is kind of like the intervals where it's increasing and decreasing, only you use the second derivative instead of the derivative. So we should begin by take the derivative. You go f prime of x. It's going to be 3x squared minus 6x, like that. This is the first derivative. And then I'm going to find the second derivative. To do that, you just take the derivative again. 3x squared becomes 6x, minus 6 becomes, or minus 6x becomes minus 6, like so. So that is the second derivative. Now I'm going to make that chart, but I make a chart of the signs of the second derivative, not the first derivative. So the chart will, sorry, I'm not ready to make the chart yet. I have to find the points to mark off on the chart. They are the points where the second derivative equals 0 or does not exist. So I set the second derivative to 0. I get 6x minus 6 equals 0. Solve this. 6x equals 6, x equal 1. So this is my only number to put on the chart. When you're doing the first derivative, this is called the critical numbers. But when you're doing the second derivative, they don't really have a special name. They're related to inflection points. But anyway, that's my point on the chart. And then that is where the second derivative equals 0. And then I'm going to plug in values like we always do, something on the left, something on the right. So point to the left of 1, I'll use 0. So it becomes f double prime of 0. And what's that? We plug into f double prime, which is here. 6 times 0 minus 6 is negative 6. So that's negative over there. And then f double prime of, let's use 2 on the right side of 1. I get 6 times 2 minus 6 is 12 minus 6 is positive 6. Positive over there. All right. And so that means where is it concave up and concave down? Those signs tell us concave up versus concave down. So I'm going to say f is concave up on the interval 1 to infinity. That's the right side where the big plus is. And then down, concave down on minus infinity to 1. Like that. All right.
I have a question.
Yes.
What would you do if
one of those, when you plugged in 0 or 2
Yep.
to f double prime, what would you do if one of them came out to equal 0?
If one of them came out to be 0, it means you messed something up somewhere else. Because in this step, I should have already found all the points where the second derivative equals 0, right? And so if one of these also equals 0, then it means somehow you missed it from over here. You should have already located that point.
All right, thank you.
Yeah. Any other questions about that one? This is just give me the intervals where it's concave up versus concave down. I didn't ask, but I could ask in a question like this. How about where are the inflection points? Any inflection points? Inflection point means one of the points, it's a point where the concavity switches from being negative to positive or positive to negative. And in this case, there is one such value. It's right, it's right here in the middle of this chart here. So I would say in this example, x equal 1 is an inflection point because the concavity switches from being down to up near the point x equals 1. All right. This, of course, I meant to say all of this is much easier if you are looking at a graph to say where a function is concave up or down. Maybe I'll just do a quick example like that. If I'm looking at a graph that looks, say, like this, maybe, and I could ask you here, tell me where is it concave up versus concave down. Well, on the picture, concave up looks like the smiley face, right? It's this shape. This is concave up. And where do you see that shape on this curve? I see it here. And I think that's the only place where I see any shape that's vaguely that type of smiley shape versus the other way around, the frowny shape, that's concave down. So that would be all of this area here is frowny, and similarly all of this area over here. So this shape is concave down. All right, that's how you can tell just by looking at a picture if it's up or down. It's a matter of this smiley shape versus the frowny shape. All right, and the points in between are the inflection points. So on this picture, I see 2 inflection points. They would be somewhere around there and somewhere around there. Those are the 2 inflection points on the picture. On the picture, it's easier. With if I just give you a formula, you got to do all that stuff that I just did. All right. Any questions about all that? All right, then the next thing I wanted to do, I wanted to just using the same example. Let's also try other kinds of questions you might be called upon in this section to answer. X cubed minus 3x squared plus 1. How about find and identify the relative extrema using the second derivative test. The second derivative test. This is another method for finding the minimum and maximum points of a function that is different from the other one that we did like last week. It's called the first derivative test. This one is called the second derivative test, and it uses the second derivative, although it also uses the first derivative. So you have to remember a little bit the technique here. You find the critical numbers first, and then plug them in to the second derivative. You find the critical numbers and then plug those critical numbers into the second derivative. All right, let's try it out. So the advantage of the second derivative test is you don't have to make any charts. You can say whether it's a minimum or maximum with no charts. That's one thing that's better about the second derivative test. I wouldn't say overall it's better or worse than the first derivative test. There's 2 different ways that you can do it. Let's do it. So first, find the critical numbers. All right, we do that using the derivative, right? Not the second derivative, but the first derivative. You do have to keep it straight in these problems, which derivative is relevant for which step. But anyway, the critical numbers is found by taking the first derivative and then setting it equal to 0. So the derivative of the original thing is 3x squared minus 6x. All right. And I'm going to find the critical numbers. That involves, like, you know, simplify here. What? Yeah, simplify. What can I do? I can factor out 3x, right? And what remains is x minus 2. And so the critical numbers, I say 3x equals 0, x minus 2 equals 0, and solve each one. X equals 0 is a critical number. X equal 2 is a critical number. All right? So these are the critical numbers. The procedure for the second derivative test, so those are going to be your minimum and maximum points. To do the second derivative test is just to tell you, is it a minimum or is it a maximum for each of those? And you plug them into the second derivative. I guess I never wrote down, what is the second derivative? Well, we did it in the previous example. You take the derivative again. I think it's most convenient to use this format to take the derivative again. It's equal to the one on the next line, but the next line has a product, which I don't want to get into the product rule, so I'm going to use that. I get 6x minus 6, all right? And so I'm going to plug these values, plug the critical numbers into f double prime, plugging them into the second derivative. I get f double prime of 0, and I'm also going to do f double prime of 2, right? Make sure you're using the correct formula. Here I said f double prime of 0, so we should be using this formula, f double prime. I get 6 times 0 minus 6, which is negative 6. When I plug f double prime of 2, I get 6 times 2 minus 6, which is positive 6. All right. These values, if you remember, how to do the second derivative test, these values tell you if it's a minimum or a maximum. So x equals 0 is a relative. And remember the rule here? If the second derivative is negative, then it is a relative. Is it a minimum or a maximum? Somebody shout it out if you know. Anybody else want to guess? It's actually a maximum. If the second derivative is negative, that means it is a relative maximum. So this, you just have to remember this fact. It's not a mystery though. If the second derivative is negative, remember what that means is the shape looks like that, all right? Which means your point is a maximum. So this is what it looks like when the second derivative is negative. It means the shape is concave down. That shape, the frowny shape, which means your point there is on the top. It's a relative maximum. And similarly, here, the fact that I got a positive here means that the function is concave up. This is the picture, what it looks like when the second derivative is positive. And so the fact that I got a positive for that second part means that x equal 2 is a relative minimum. All right. This is the rule for the second derivative test. You just have to remember that when it's negative, when the second derivative is negative, you get a maximum. When the second derivative is positive, you get a minimum. Any questions about that? And if you get 0 at this point, it means that you don't know if it's a minimum or a maximum. This is the big kind of downside to the second derivative test. Sometimes the second derivative test just straight up doesn't work. If in this step you get 0 when you plug into the second derivative, then you still don't know. It might be a minimum or a maximum, and the only way to find out is to use the first derivative test, where the increasing decreasing thing. That's kind of a bummer when it happens. All right, I think that's enough of that then. Let's talk about the last topic this week is about curve sketching. So a problem like that would say something like, draw the graph of, and let's just use the same example, x cubed minus 3x squared plus 1. Draw the graph. All right, let's see if we can do it. The basic strategy for this would be, again, find the critical numbers, make the chart concerning increasing and decreasing, and then I would say the next step would be to plot the critical numbers. on your graph and then connect the dots. If this is mysterious, we'll do an example. You'll see what I mean by all of these things. All right. The goal here is to draw the graph without using your calculator, your graphing calculator or whatever, and without just like plotting every point. That's we don't want to have to do that. Draw the graph. So let's just follow the little advice that I said. We should find the critical numbers and make the increasing decreasing chart. Now we've already done most of this work already from the previous, the other questions. They all involve similar collections of information, right? F prime of x is 3x squared minus 6x, and if you simplify this, you can factor 3x and x minus 2, right? This we did before, and the critical numbers are 0 and 2, just like before. One thing that we never did before was to make that increasing and decreasing chart. So let's do that. I'm going to put 0 and 2 on my chart here. And using the first derivative to tell if it is increasing or decreasing, we plug various values in to the first derivative. So to the left of 0, I'm going to do f prime of minus 1. Plugging in right here, right, this is f prime. I get 3 times minus 1 times minus 1 minus 2. This is a positive, a negative, a negative. So this is going to be positive over there. All right. Next, let's do in between 0 and 2. I'm going to use 1. So f prime of 1, I get 3 times 1 times 1 minus 2. This is positive, positive, negative. So I get a negative in the middle there. It's 0 in between, of course. And then finally, to the right of 2, I'll use 3, f prime of 3. 3 times 3 minus 2. Those are all positive, so I get positive over here. All right. I'm sorry, can't see it. So this is the chart of increasings and decreasings. This is going to be our principal guide to what shape the curve is going to be as we're drawing the curve. All right. Okay, so as far as the little steps, my advice here, find the critical numbers, did that. Make the increasing, decreasing chart, I did that. All right, plot the critical numbers on a graph. So in order to plot these, we need to find the y values for the critical numbers. And you got to keep it straight here, which equation you're using in which part. To find the y values, we plug the critical numbers into the original formula. So we use f of x, not the derivative, not f prime of x, not f double prime of x, certainly. To find the y values, we use f of x. So I'm going to do what is f of 0 and what is f of 2, right? Those are my critical numbers, 0 and 2. And I'm going to use the original function. That's this, right? So we plug the numbers in. Sometimes you have to use a calculator in this step, although on a test or something, I will make the numbers easy enough for you to plug in. What is f of 0? You go up to that formula all the way at the top and plug in 0 for x. I get 0 cubed minus 3 times 0 squared plus 1 is 1. All right, that was easy enough. I like 0. How about f of 2? You plug 2 in there. I get 2 cubed minus 3 times 2 squared plus 1. What is that? I need to know the real answer here, not just a sign, because I want to plug this, plot this value on my graph. 2 cubed is 8 minus 3 times 2 squared. 2 squared is 4 times 3 would be 12. So it's 8 minus 12 plus 1. What is that? Negative 3, I think. All right. So that means my critical numbers, in terms of like x and y values, they are 0, 1, because x equals 0 gives me the y value of 1, and 2, minus 3, because x equals 2 gave me the y value minus 3. How am I doing? Any questions so far? These ones are pretty, there's a lot of work to make your way to the answer.
I have a quick question.
Yes.
So, was this meant to be for like this week, and like the asymptote one was for next week?
Yeah, that's right. So I mixed up the links.
Okay. So like the work that some of us possibly did for next week. We just like ignore that for the quiz tomorrow.
Yeah, I suppose. I mean, it's the same stuff. That's like a harder version of this.
Okay.
Yeah, and you'll get to it next week. So,
All right.
yeah, sorry for the confusion. All right, we're almost done with this problem here. I have my two critical numbers along with their y values, and I'm going to start drawing the graph now. All you need really is these points here plus this chart here. So everything else is not going to be relevant for us anymore. So I'm going to draw my graph here. We begin by plotting the critical numbers with their y values. So my critical numbers are x equals 0, y equals 1, which I will put right here. That's the first one. And the other was 2 comma negative 3. So 1, 2, and then 1, 2, 3 down here. 2 comma negative 3 is like that. All right. And now just to help myself remember, these are critical numbers. That means that the derivative is 0 at those 2 points. So I'm going to indicate that by putting like a little sort of horizontal line. This is to remind myself that the derivative is 0 at those 2 points. That means when I start drawing the curve, whatever it is, it must enter and leave those points going horizontally. All right. So let's talk about then, how do we draw the graph? You know, the last thing I said in terms of my advice over here, I said plot the critical numbers. I'm looking up here. Plot the critical numbers and then connect the dots. What does that mean? Well, over here, these 2 dots are part of the graph. I need to draw the curve that connects them. Now, there are many ways you could draw a curve in between those 2 dots. For instance, you could do just like that. That is not correct. I mean, this function is not just a straight line, so you shouldn't be connecting the dots using straight lines. One reason I know for sure that's not correct is because I said before, this curve, when it enters this point and this point, it should be traveling horizontally when it touches those points. And this is not. It's just going in a straight line. So that was definitely wrong. I'm going to get rid of that. What does it look like? Well, there's really only one thing that it could do. If it's going to enter these points horizontally, it has to, and then, sorry, together with the chart of increasings, decreasings, you will see in this region of the graph here, between x equals 0 and x equals 2, I look here and I see that the function is decreasing. That means from this point, it needs to come out of this point horizontally and then decrease until it gets to this point, which it enters horizontally. The curve must look like this. All right? You make the curve go, it enters and exits those points horizontally, and it has to be decreasing the whole time. All right? It cannot have any other funny business, any more ups and downs. It can't do something like this, because that would have extra critical numbers in between it, but it's not. It has to be decreasing throughout that entire region, so it must look like that. All right. This is the idea. We're not done yet. We need to draw something over here, right? The curve has to do something. So think about as you leave this point and proceed to the right, what should happen? Well, first of all, you should leave going horizontally, but then it's going to either start to increase or start to decrease. And what should it be? Any thoughts here? Somebody shout it out. As I leave this point and go to the right, should it increase or decrease? Go up or go down?
Increase.
It should increase because of the chart here. So you look at this chart will guide you as far as should I go up or down. The answer is you should go up, in this case, to the right of this point. So you should come out of this point horizontally, but immediately start going up. So it looks like that. And it should continue going up forever, right? Because that's what the chart says. It says it's going to be increasing on the right side there. All right. And finally, what about this point? You got to think about what happens to the left of that point, right? As I exit this point, you are going to exit going horizontally. But then should I go up or down? Now, this can be a little bit tricky. The chart over here says that the function is increasing, right? The function is increasing. That means over here, it needs to go up until it gets to this point. So it goes like that. It has to be increasing until it arrives at that point right there. All right. I said this, I don't know if that sounded confusing to you. I said it can be confusing if you think about, what if I'm at this point and I travel to the left? Should I go up or down? You might be tempted to say I should go up because of the increasing. But remember, when we say increasing, decreasing, we're always talking about moving a lot across the picture from left to right. So as in this case, over here, as I move from left to right, it should be